So last time we were doing this example with one-sided limits, so I'm going to pick it up right here, and I'll also review the concepts for one-sided limits and stuff. Okay, so in this example, one of my goals is to, explain when we need to use one-sided limits and when we can just do the two-sided limit directly. So certainly for this first problem, there's no guessing involved. We're clearly told for this first limit to do a one-sided limit from the left. That's what this little minus sign means. Then we're asked to do a one-sided limit from the right. So this is a limit from the right. That's what this little plus sign in the upper right-hand corner means. And then finally, this limit here where there's nothing specified on one, that's a two-sided limit. So here we need the limit from the left and the right to be equal and to be finite. So before I get into this example, let me draw an x-axis here, and let's think about how the function is built here. So right here, I'm going to put, let's say, put 1 right here. So right here we have 1. And right here, I guess let me stick 2. So here's 2. So now if you look at the function, in this section, for x less than 1, in this section, whoops, let me change the color here. In this section here, for x less than 1, we know the function is defined as 3x. Okay. And in this section here, between 1 and 2, we know this is defined as 2 plus x squared. So for this first limit here, where I want to do the limit as x goes to 1 from the left, here, if I'm approaching 1 from the left, you can see we're in part of the domain where the function is defined as 3x. So right down here, where I'm trying to do this limit as x approaches 1 from the left, I'm using the fact that if x is less than 1, then the function looks like 3x. And so that's exactly where this comes from. And to actually calculate this limit right here, I'm now plugging in numbers closer and closer to 1, but from the left, i.e. less than. And so that's what's happening in this table up here. So if you look up here, I have numbers that are less than 1, to the left of 1, but approaching 1, getting bigger and bigger. And I don't actually plug in the numbers and calculate it with a calculator. Like I'm not actually calculating these numbers. We're just looking at the trend and trying to figure out the pattern. And based on this pattern, 3 times 0.9, 3 times 0.99, 3 times 0.999, we see the pattern is gonna go to 3 times 1 because 0.99999 eventually will hit 1. And so here we can conclude that the limit from the left is 3. And now for the limit from the right, oh no, I erased my little stupid thing. For the limit from the right here, look at the value of the function from the right. So here, when we say from the right, we mean x has to be bigger than 1. And when I say x bigger than 1, so this part's important. In a limit, we want to look at x bigger than 1, but very close. So certainly, some folks might be saying, well, if x is bigger than 2, then it's bigger than 1. And I agree with you. But in a limit, we want to stay as close to 1 as possible, but here be slightly bigger. So in this case, this is actually the region we're in, where x is to the right of 1, but still very close. And in this region, the function definition is 2 plus x squared. So in this region, the function looks like this. And so this is exactly where this 2 plus x squared came from. And if you look on here, let me try and do this quickly. So here's 1, here's 2. So 1. So remember, in this section, it's 3x. But in this section, it's 2 plus x squared. And now we're trying to do a limit from the right here. So I need to use this function 2 plus x squared. That's right here. That's why there's a 2 plus x squared right here. And so now we're plugging in. We're plugging in numbers closer and closer to 1 into x squared, but slightly larger. And, you know, we can think 1.1 squared, 1.01 squared, 1.001 squared. It's getting closer and closer to 1 squared. So we get 2 plus 1 squared. So we get the limit here is 3. And, you know, here we did this one-sided limit to the right. In the first limit we did was the one-sided limit from the left. For the two-sided limit now, we look at the limit from the left and the right and we say, are they equal? And so, you know, if you look, the limit from the left is 3. The limit from the right is 3. Because they're equal, so these are the same, we can conclude the two-sided limit exists and the two-sided limit is equal to 3. If the limit from the left and right weren't the same, you know, then we'd have an issue. For x approaching 2 from the left. So for this next problem, actually, let's look at the original problem statement. They just ask us to find the two-sided limit. People pronounce that as just the limit, but be careful, that's a bit misleading. So here we want the two-sided limit. My real question is, when do we look at the one-sided limits and when can we do the two-sided limit directly? So if you look in this case, we're going to have to use the one-sided limits because the function, right, from this region, for x greater than 2, there's a different function definition. For the function in this region, it's defined as 1 over x cubed. And so look, if I want to do a limit, a two-sided limit approaching 2, so then when I approach 2 from the left, the function should be 2 plus x squared. But when I take the limit approaching 2 from the right, actually, sorry, let me use this green color. Take 2 from the right, look, it's a different function. Coming from the right, I have to use 1 over x cubed. But coming from the left, I have to use 2 plus x squared. So that's what you see here. For this limit coming from the left, so here, x approaching 2 from the left. Now look, if x is less than or equal to 2, but very close, the function we want to use is 2 plus x squared. And if you plug in 2 here, x squared, you know, 2 squared is 4, 4 plus 2 is 6. That's exactly where this limit came from. X approaching 2 from the left, x is less than 2, but still very close. So I use the function 2 plus x squared. Now plug in 2 for x squared. 2 plus 4 is 6. For the other function, here we're approaching 2 from the right. So I need to look when x is bigger than 2. And so you can see when x is bigger than 2, I want to use 1 over x cubed. And now I plug in 2 for x, right? Because I send the limit to 2. So 1 over 2 cubed is 1/8. And so, you know, because the function changes its definition around 2, here I had to look at the one-sided limits. And because the limit from the left equals 6, and the limit from the right equals 1/8, the limit from the left doesn't equal the limit from the right. So the two-sided limit does not exist. So here I say the two-sided limit as x approaches just 2, there's no minus or plus. I say DNE for does not exist, because from the left it's 6, from the right it's 1/8. So the one-sided limits exist, but the two-sided limit does not, because they're not equal, the one-sided limits. For this third limit here, so I want you to think, do we need to use two-sided limits or can we do it directly? If we look at 3, so let's look at the definition of the function at 3. So here's my x-axis. Here's 3. Here's the number 3. Here's 2. So actually, let me do it this way. Let me put it on top. Here's 3, and here's 2. According to the function definition, once for this entire section here, the function definition here is 1 over x cubed. But here for our limit going to 3, if you look, if I take a limit from the left, but very close from the left, the function definition stays the same. If I take a limit from the right, the function definitions in both cases, the function definition is always 1 over x cubed. So in this case, we don't need to do the one-sided limits. In this case, we can check the two-sided limits directly. And so I'm just going to take 1 over x cubed and plug in 3 for the x cubed. So here the limit of f of x as x approaches 3 is 1 over 3 cubed, or 1 over 27. So for this limit x approaching 3, we did not need to check the one-sided limits, but for the limit approaching 2, we do need to check the one-sided limits because the function changes its definition around 2. If x is less than 2, there's one definition, and if x is greater than 2, there's a different definition. And this limit, this two-sided limit of x going to 1, again, here you need the one-sided limits because, again, the function changes its definition. Whether x is less than 1 or bigger than 1, the function definition changes. Here for x equal to 3, the two-sided limit at 3, we don't need to look at the two-sided limits because the function has the same definition, whether you're to the left or to the right. Okay, so I hope, that's something really important to appreciate. When do we need to use one-sided limits and when can we do the two-sided limit directly? The function's changing its definition, then we need to look at the one-sided limits. So for the fourth part, I want to emphasize that the limit is different from the function values. So here for f of 1, if you look at the definition of f of 1, there is no definition. They've literally left it undefined. This is x less than 1. This is x greater than 1. There's literally no definition given for x equal to 1. So the function is literally undefined for x equal to 1 or does not exist. And in the graph, for x equal to 1, you would not plot any point for the height over x equal to 1. So here, they literally left, x equal to 1 undefined. At that point, there's no output. For f of 2, in the case of f of 2, the function has a definition. So we can see when x equals 2, we should use this as our definition. So now I'm going to take 2 and plug in 2 for x. 2 squared is 4, so f of 2 is 6. By the way, in the first case, f of 1 did not exist, but the limit approaching 1 did exist. In this case, f of 2 exists, but the limit, the two-sided limit approaching 2 does not exist. And for the third case here, For f of 3, based on the function definition, if x is greater than 2, and certainly 3 is greater than 2, this is the function definition we want to use. And so I'm just plugging in 3 right in for x cubed. And so f of 3 is 1 over 27. Note that in this case, the function is defined and the limit exists and they're equal. In the second case here, f of 2 is defined, but the limit does not exist in this case. Look. In the very first case here, the function's not defined, but the two-sided limit is. So I wanted to highlight the difference between the limit and the value of the function at the point. And we'll keep talking about that. We'll come back to that. So let me talk about average rates of change and instantaneous rates of change. So actually, an instantaneous rate of change is a derivative. So we've actually already gotten to a derivative, which is good because this is calculus. So the first thing I want to talk about is we can rewrite the limit. So for example, we're going to do, there's a very common variable change that we use where we rewrite the limit of f of x as x approaches a as the limit of f of a plus h as h approaches 0. So let me show you how we get this, okay? It's not that hard, but it's a little confusing if you haven't seen this before. So start with this limit of f of x as x approaches a. Now, what I want to do is I want to introduce a change of variables, okay? So this is something that's very commonly done in calculus. So if you're like, how do we know to do this? This is something that someone else has worked out many times before, okay? So I'm going to introduce this new variable called h and let h equal x minus a. So now I want to convert the limit. So the limit was originally in the variable x. I now want to make the limit in this new variable h. Remember, a is a constant. So first thing I need to do is I need to replace x. So using this equation here, you can solve for x. So look here, if you move the negative a to the other side, you get x equals a plus h. Sorry, let me fix my plus here, a plus h. So this x here gets replaced. And now, since h equals x minus a, think about if we send x to a, like we're doing right here, if we send x to a, this whole thing will go to a minus a or 0. So down here, when x is going to a, that's the same as h going to 0. So it's a little tricky. So the two things that you need to make this work is one, solve for x. So x is a plus h. And then two, in here, think about what happens to h as x goes to a. So we solve for x, we get a plus h. So that's where this a plus h is coming from on the right-hand side here. And when x goes to a, h goes to 0. So that's where this limit h goes to 0 is coming from on the right-hand side here.
Is
Anyway,
it?
Yeah, go ahead.
So is it always going to be as h approaches 0?
If we let h equal x minus a and send x to a, then yeah, h will always go to 0.
Okay.
So now we define what's called the average rate of change. So here, for average rate of change problem, two pieces of information need to be given to you. One is we need to be given a function, and the other thing is we need to be given an interval. So here, if someone says, what's the average rate of change of a function, they need to give you, you need to say, well, over what interval? They can't just say, what's the average rate of a function? So for the function f of x And let me draw a picture here just so we can kind of think about from a graph point of view what's happening. So let me do like just like a simple function like a parabola or something. So here's something just like this. And so let me pick some points A and B. So here's A and here's B. And here's the height. So what we're doing, if you look at this formula, first of all, it looks like a slope formula, but here f of x may not be a straight line, so this may not be a slope. Okay, so be careful. Like in the picture I've drawn, it's not a slope because f of x is not a straight line. So here's f of b. Okay, so here's f of a, and here's f of b. So basically when we calculate this number, it's taking the height change. So f of b minus f of a is exactly this height. F of b minus f of a is the numerator, exactly this height. And it's taking the total height change and dividing it evenly over the x distance traveled. So, you're just kind of trying to find, if we were to increase the height in a very steady, equal way from A to B, how do I get from f of A to f of B? So suppose, for example, f of A is 2, and suppose, for example, f of B is 10, and here, suppose, for example, A is 1, and B is 3. So here the height change, it changes 8 units. There's an 8-unit height change. From A to B, it increases 8 units. And this is over a horizontal distance of 2 units. So basically, for each unit of x, there's an average increase of 4, the average height increase of 4 units. So from A to B, there's some 4-unit increase from 1 to 2, there's a 4-unit increase. From 2 to 3, there's another 4-unit increase. And it's taking the height increase and evenly distributing it. Even though that may not be true of the function might be doing something not even at all. For example, our function could look like this. The function could look like, it could be flat this whole time and then suddenly shoot up. In both cases, the average height increase is 4. We're just trying to evenly distribute that height increase over the horizontal increase. So the whole reason we talk about average rate of change is because we really don't want to know what the rate of change in an interval is. We actually want to know what the rate of change is at a specific point. So now, instead of looking at the interval A to B, now let's look at the average rate of change over the interval A to X, where X is a variable and X is bigger than A. So then that average rate, just the average rate of change part, would look like this. So here, this expression here is exactly the same as this expression up here. They're both the average rate of change. The only difference now is I've made what was before a fixed constant, what was b before, which is a fixed constant, I've now made it a variable x. So instead of b, now I have x, a variable. And this calculates the average rate of change. What I want to know is not the average rate of change over the interval a to x. I want to know the average rate of change over the interval a to a. I'm trying to find the rate of change at a single point, not over some stretch of distance. And so that's where this limit comes in. We send x to a. That'll calculate not the average, but the instantaneous rate of change at a single point, as opposed to the average rate of change over an interval. That's really the big difference, that we're calculating how something is changing instantaneously. in the exact moment. And this thing here will be called a derivative, which we'll talk about more in chapter 2. But this starts to introduce the concept of the derivative, and we'll talk about instantaneous rates of change, a whole lot more. So I did a very quick example here where first we're given some information that if you drop an object, it travels 16 t squared feet per second. So that's just basically a position function from physics. And so here we've dropped a rock from a 150-foot cliff. In this case, the height of the cliff doesn't matter, so I'm just asking for an average velocity problem. So it says, what is the average velocity of the rock during the first 2 seconds? So the main point of this example for me was just to remind you of this formula where distance equals rate times time. And so here, when they talk about average velocity, think about when you're driving in your car, what's your velocity? 50 miles per hour. Miles per hour is distance per time. So here, when they're asking for average velocity, they're asking for a rate. And rate, distance equals rate times time. So rate equals distance over time. And so I'm going to use this distance over time formula to find this average velocity. So here, velocity is distance over time, or rate is distance over time. And here, if you want to rephrase this question, asking us to find average velocity is the same thing as asking us to find the average rate of change of the distance over this time interval 0 to 2. Because you should connect up, velocity here is actually distance over time. And so that's what I'm doing in my equation. So delta y would be the change in our distance over delta x is our change in our time. So here would be f of b minus f of a. In this case is f of 2 minus f of 0 over 2 minus 0. And then I plug it into the function and do the math. And here, there's a 2 squared. Downstairs you have a 2, so you can cancel a 2. 16 times 2 is 32. So, next time, or in a couple of days, we'll want to not know the average velocity over 2 seconds. I want to know what's the exact velocity when we're at t equal to 2 seconds, not over an interval. What's the exact velocity when we're at t equal to 0 seconds? Not between 0 and 2, not between 0 and 1, but exactly at 0. So to find that answer, we'll need a limit. And that's why we've been studying limits. And ultimately, we will see that a limit is a special type of a derivative is a very special type of a limit. An integral turns out to also be a very special type of limit. So at the end of the day, Calc 1 is all limits. And in Calc 2, there's a huge portion called sequences and series, which is also all limits. So it's incredibly important that we get our limits in really well, get a really good foundation on limits. So this ends section 1.3. So I'm going to switch over now to section 1.4 and start talking, as I said, about techniques of how we actually calculate limits. I said limits are important. So now these are the techniques you're going to need. Okay, so these are the practical nitty-gritty, how do you actually solve a limit? Okay, so here we have some very important limit properties for convergent limits. Remember, we say a limit is convergent if it exists, and we say that a limit exists if it equals a finite number, right? So here, in this case, we have two convergent limits, say limit of f of x as x approaches a equals L, where L is some finite number. And then we have another limit, say limit of g of x as x approaches a equal to m, where m is some finite number. And here, remember, I keep saying limits, but you should always keep in mind these are two-sided limits, okay? So if we have two convergent two-sided limits, then we have the following algebra of limits. The limit of the sum f plus g equals the sum of the limits. So here, from the left-hand side to the right-hand side, what you should appreciate is on the left-hand side, we do the addition first, and then we take the limit. On the right-hand side, we are doing the limits, and then we're adding those limits. So here, the order of operations has changed. In one case, I'm doing the sum first, then the limit. In the other case, we're doing the limit first, then the sum. when the limits exist, they're the same. We have a similar property for the difference. The limit of the difference is the difference of the limits. And similarly for the product, the limit of the product, f times g, is the product of the limit of f times the limit of g, which is equal to L times m. Finally, the limit of the quotient, f divided by g, is the quotient of the limits. So we have limit of f divided by limit of g, which is L over m. Of course, because m is in the denominator, we require that the denominator is not 0, provided m is not equal to 0. So the limit also can be brought inside powers and roots. So here the limit of f of x raised to the nth power, and then we take the nth root. That's the same as the nth power and the nth root of the limit of the function. And so again, you should see the order of operation of the exponentiation and the limit have been reversed here. And if n is equal to 1, then the limit of f raised to the m will be just the limit of f raised to the n. Two final equivalencies here. This, if f of x approaches L as x goes to a, then the absolute value of f of x minus L, the distance between f of x and L, will go to 0. And these two are equivalent. Remember we talked about logic last time? This is an if and only if. These two limits are saying the same thing. If f of x approaches L as x approaches a, then the distance between f of x and L will go to 0 as x approaches a. So think about that. One limit is talking about the actual output value of the function in the range approaching another value. The other limit is describing the distance between points in the range, okay? One final comment here before we start doing some limits is, in a limit like this where we're sending x to a constant, so remember here, little a is a constant. In a limit like this, the actual variable doesn't matter. So the limit of f of x as x goes to a would be the same as the limit of f of z as z goes to a. In both cases, we're taking our variable, whatever squiggle you're using, you're taking that squiggle and sending it to a constant a. In both cases, the squiggle eventually gets replaced by the constant a. Okay, so the actual variable in a limit is not important when you're sending the variable to a constant. So this is kind of a conceptual thing, It's not a complicated thing, but it's important that this makes sense to you from a conceptual point of view, that you start to really just treat squiggles as placeholders. Doesn't matter in this limit if the squiggle I'm using looks like an X or if the squiggle I'm using looks like a Z. The point is it's just a placeholder. Okay, so this next property is our number one go-to strategy for doing a limit. Okay, so it's in two steps. First, I recognize I'm doing a limit problem, as opposed to what? In Calc 3, we're either doing limit problems, derivative problems, or integration problems. Right now, it's easy. We've only done limits, but I still want you to start to analyze the situation that way. So here, once we know it's a limit problem, the first thing to try and do is just plug in the number, okay? So here the book calls this the direct substitution property. For polynomials and rational functions, to find this limit, the limit of f of x as x goes to a, all you need to do is plug in a into the function. The way I like to think about it is that we're bringing the limit inside the function. So that's why I kind of have an extra line here. So here I'm thinking of bring the limit inside. And then when you take this limit of x as x goes to a, that goes to a. Okay, so the book just writes it this way. They don't include this center part. Whoops. Why is that not working? Oh yeah. The book doesn't include this part right here. The book just says the limit of f of x as x approaches a equals f of a. So this is called the direct substitution property. This is the first thing we try when you have a limit. When you plug it in and if everything works out and you get a nice number, then you're done. We move on to the next limit. So let me do some easy limits here in this first slide. And then we'll talk about what do you do when you have more tricky limits when just plugging in doesn't work. Also for this first limit's very easy. Limit of 2x plus 9 as x goes to 3. You simply plug in the 3. 2 times 3 is 6. 6 plus 9 is 15. This limit will be 15, okay? But I've done it in a very explicit way because I want to show you the properties at work. And I think there's 1 or 2 homework problems where they want you to be very explicit and show exactly how the properties are working at each step. So here, look, the limit of the sum is the sum of the limits. And now the limit of this product is the product of the limits. And you see why the limit on x is the only one that really matters. Because for the constants, they don't change their behavior. This is just going to be 2. This is just going to be 9. So finally now I send the limit and we do the calculation. And so the limit's 15. Like I said, this was not a hard limit. I just want you to see the properties at work very explicitly. So again, here's another limit. Oh, by the way, you might have a typo on your slide. I think I had a typo right here. I had this written as x goes to -1 and I corrected it. And so I'll re-upload these slides with that corrected, and my apologies for that. For this next limit, x going to -1, a two-sided limit, positive square root of x squared plus 8. Again, this is not hard. We take -1, plug it in. -1 squared is 1. 1 plus 8 is 9. The positive square root of 9 is 3. So this limit will be 3, but I just want you to explicitly see the properties at work. So here, I bring the limit inside under the root. Then the limit of the sum is the sum of the limits. Then the limit of x squared is the square of the limit of x. And then finally, you can do the limit and do the math. And as we said, we got +3. So I just want you to explicitly see, if you're doing this on a test or something, I wouldn't expect you to do all these steps in the middle. For this problem, it's so easy. I'd expect you just to go from the first step to the last step here, if you're doing this on a test. But here specifically, I'm trying to explicitly show you how, these subtle little properties we're using, how they get used, okay? For this one, again, it's not easy. I mean, it's not hard, okay? But I just want you to think about, if you were doing this, I would just plug the -1 in and calculate it. But here's, if you really want to keep track of all the properties, here's what's happening. The limit of the quotient is the quotient of the limits. In the denominator, the limit of the sum is the sum of the limits, and then I brought the limit inside under the square root. So I skipped a step because I'm getting tired of showing every single step. Finally here, I should do the limit of the sum, but I think I got tired and I just plugged the -1 into the x squared. And so then you get -2/6 when you do the math, which simplifies to -1/3. Okay, so for this, the very first thing you should try when doing a limit is try and plug it in. That's absolutely the very first thing you should try. If it works out and you get a nice number, you're probably good to go. Now, suppose you plug in the number and you get something like 0/0. This is known as an indeterminate form. And what you should think of 0/0 as the math is giving you feedback. The math is telling you something weird is happening here. And in this case, we need to do further analysis by using some other mathematical strategy. So in this case, if you get 0/0, we need to try some other mathematical strategy, which I will discuss with you in a second. The other indeterminate forms which you should memorize, along with 0/0, is infinity over infinity and infinity minus infinity. Okay, so we'll talk about more of the infinity-based indeterminate forms in section 1.6 on Monday, okay? But for these cases, some strategies you can try when trying to do the limit. So remember, these are limit strategies. This is for when you're trying to do a limit. You plug the number in, you either get 0/0, infinity over infinity, or infinity minus infinity. Then you can try to either algebraically simplify. So usually the algebraic simplification involves factoring and canceling, or combining terms. Like if you have two fractions, typically when you have a couple, two fractions, one trick to try and do is to combine the fractions into a single fraction. And I'll show you an example here in a second on the next slide. Another strategy might be to multiply by the conjugate. And I'll remind you what the conjugate looks like. Another strategy might be to use the squeeze theorem, which we'll talk about in class on Friday. We won't get to the squeeze theorem today. And another strategy is known as L'Hopital's rule. If you've had calculus, then you've heard of L'Hopital's rule. So that'll be discussed in section 5.8 at the very end of the semester. And remember, you cannot use L'Hopital's rule up until that point. So even if you know L'Hopital's rule, I'm sorry, but you can't use it unless you can prove it. So here's a limit problem. So we have the limit of x to the fourth minus 81 over x minus 3. You know, the limit is x goes to 3. So I go, it's a limit problem. The first thing I'm going to try and do is plug in the 3. If you plug in 3 for x to the fourth, 3 to the fourth is 3 times 3, which is 9, times 3 times 3, 9 times 9 is 81. So I get 81 minus 81 divided by 3 minus 3. So here I get this indeterminate form 0 over 0. This is feedback. This is the math telling me I need to now try some other further mathematics. Now, here's the part. It's a case-by-case basis. By observation, looking at the numerator, my spider sense tells me, hey, we can factor this because this is a difference of squares. Remember, x to the fourth is x squared squared. And 81 is 9 squared. And we can factor a squared minus b squared is a minus b times a plus b. So here I factor the numerator. And then I try to plug in x equal to 3 again. But we get 0 over 0 again one more time. So again, I get 0 over 0. So when I get 0 over 0, I usually write it, you know, over the equal symbol. It also makes a little face there. You just got 2 eyes and nose. It's nice. It's my friend. So what do? You know, we don't panic. We notice that this can be factored some more. Again, a difference of squares. So here now, I factor x squared minus 9 as x minus 3 times x plus 3. And now you see things start to work out. Now the x minus 3 in the denominator, I can cancel with the x minus 3 in the numerator. And now we have just this nice expression. Now try to do the limit again. Just plug in 3 and see if it works. If it works, you're done. If you get an indeterminate form, we try something else. However, in this case, it's such a simple function, no problem. Everything works. We get the limit's 108. So it all starts from me identifying it's a limit. When I get the indeterminate form, I then know some strategies to try. Okay, so let's do the next limit. I have the two-sided limit of the positive square root of x squared plus 8 minus 3 divided by x plus 1 as x goes to negative 1. In the denominator, obviously, we have 0. In the numerator, minus 1 squared is 1, plus 8 is 9. I'm going to remind you, this is the positive square root, right? So the positive square root of 9 is positive 3. 3 minus 3 is 0. So again, in this case, we get the indeterminate form 0 over 0. So now, you know, here I'm not trying factoring. Here, based on this expression, positive square root of x squared plus 8 minus 3, that gives me an idea to, can I get rid of the square root? If we multiply this thing by the conjugate, do you remember the conjugate, folks? So here, the conjugate of square root of a plus b is square root of a minus b, and the conjugate of, you know, square root of a minus b is square root of a plus b. The conjugate is square root of a plus the square root of anything is the square root of whatever minus the square root of blah, and vice versa. And we're taking advantage of the fact that a minus b times a plus b is a squared minus b squared. So here, you should think of this one, this term here, this is my, you know, a minus b times this term here is a plus b. And so you get a squared minus b squared. In this case, a squared is just the positive square root of x squared plus 8 squared. So this term here, when you do a minus b times a plus b, this term right here gets squared. And then minus 3 times plus 3 is 9. And then we have to do the simplification here. 8 minus 9 is minus 1. And so at this stage, okay, now let me try the limit again. I didn't want to do too easy a problem, so I made it so here, when you try the limit again, once again, we get 0 over 0. Once again, we get an indeterminate form. Okay, I wanted to do a slightly trickier problem. But again, now, if you examine it very carefully, I hope you notice, look, in the numerator, we can factor it. So now I factored as a difference of squares, and now things start to work out. I can cancel this x plus 1 from the numerator and denominator. Now plug in the -1. In the numerator, I get -2 divided by, in the denominator, positive square root of x squared plus 8, put in a -1. 1 plus 8 is 9. Positive square root of 9 is 3. You get 3 plus 3. I get a -2/6. So this will simplify to -1/3. And that's my final answer here. So, the 0 over 0 or infinity over infinity is just feedback that we either need to do some factoring or multiply by the conjugate. Like I said, if you had two fractions, you would try and combine them into a single term, so it all depends to some extent on the limit, but there's only so many situations I can give you. I can't give you a situation that doesn't involve factoring or multiplying by the conjugate. I mean, there's only so many situations for these things. So here's a third scenario that's not algebraic simplification or multiplying by the conjugate. So I'll finish up this example and stop here, okay? So here, let's read the limit. It's the two-sided limit of the absolute value of x minus 2 over x minus 2 as x approaches 2. Here, obviously, when you plug in 2, we get 0 over 0. In this case, the trick or the strategy is to look at the one-sided limits. And I want you to understand why. Because remember, if we look at the graph of absolute value of x minus 2, the graph of absolute value of x minus 2, so the -2 shifts it to the right 2 units. So the graph looks something like this. So look, if I do a limit from the left, that's a different function than if I do a limit from the right. You see this function here, is different from this function here. So for this two-sided limit, I actually have to look at it from each side. Okay, so what I'm going to now do is let's write down the definition of the absolute value of x minus 2. This is a very important skill that you need to be able to do, to write down what's the definition of absolute value of x minus 2 or absolute value of anything. So first, remember the definition of absolute value of A, the absolute value of blah is equal to blah if blah is greater than or equal to 0. It's equal to negative blah if blah is less than 0. In this case, replace the A with x minus 2. Absolute value of x minus 2 is x minus 2 if x minus 2 is greater than or equal to 0, and is negative blah if blah is less than 0. One final step, solve for x. Move this -2, move it to the other side. Move this -2, move it to the other side. Okay? So the definition ultimately that you should be able to come up with is this. You should be able to say absolute value of x minus 2 equals this. And now let's plug it in. So now I'm going to take this definition and plug it in up here. I'm basically going to divide by x minus 2. So if I divide x minus 2 by x minus 2, we just get 1. If I divide negative x minus 2 by x minus 2, we get -1. And look, because I'm dividing by x minus 2, I have a domain restriction. Since x minus 2 is in the denominator, remember x here cannot equal 2. And you'll see in my definition, I dropped the equal symbol. The equal symbol is no longer there because I know now I have a x minus 2 in the denominator, so I can't include x equal to 2 anymore. All of these steps are crucial that you be able to work with the absolute value. So now we can do the limit. If I take the limit as x approaches 2 from the right, x approaches 2 from the right, here absolute value of x minus 2 just looks like x minus 2 over x minus 2, cancel, cancel, the limit is 1. And the limit as x approaches 2 from the left, absolute value of x minus 2 when x is approaching 2 from the left is negative x minus 2. And so now here, cancel, cancel. The x minus 2 I cancel. Top and bottom, the limit's minus 1. So the limit from the right is plus 1. The limit from the left is minus 1. What do you say about the two-sided limit if the one-sided limits aren't equal? Two-sided limit does not exist. Because this limit and this limit not equal. So this slide is very important that you be able to manipulate the absolute values. Okay, all of the absolute value stuff that we did on this slide, that's something you should review and work on and double check. And I have a final general comment here it's the same problem. Instead of shifting it by 2, it's just at the origin. Absolute value of x over x is x approaches 0. It's identical, same problem. All right, everybody, I'm going to stop right here.